Okay, good evening, everybody. My name is Alan Armstrong. I'm the current head of the Department of Chemistry here at Imperial. I'd like to welcome you all to the inaugural lecture of Professor Paul Lickiss. A particular welcome to external guests, including Professor Alan Bassendale, who will give a vote of thanks following the lecture, and to Paul's family, who is great to have here celebrating tonight as well. A bit of introduction about Paul for those of you who don't know him. Well, there probably aren't many of you, but just in case. Paul's scientific career started at the University of Sussex with a BSc in chemistry in 1980. Then he stayed at Sussex to take a DPhil in 1983, working with Professor Colin Eborn, a well-known expert in the field of silicon chemistry, which I guess is where Paul's career-long love of silicon came from. And then he did a postdoc position for a year in Toronto with another giant in silicon chemistry, Professor Adrian Brook, who's known even to organic chemists for his famous rearrangement reaction. And then he came back to the UK and back to Sussex as one of the first Royal Society University Research Fellows. And he stayed in that post in Sussex for 3 years before moving to Salford as a lecturer in 1989. And then in 1993, when David Phillips was head of department, we were looking for new young blood for the inorganic chemistry section, and we made 2 appointments at the same time, both with a Sussex pedigree. So one of them was Tom Welton, who of course is now our Dean of the Faculty of Natural Sciences, and the other was Paul. And over the years since then, Paul has proved to be a really tremendous colleague. He's a top citizen in the department. He's been our guru in terms of infrastructure, keeping our buildings running. And most recently, he's an absolute hero in terms of planning for our new building, the Molecular Sciences Research Hub on the new White City campus. And we're all really grateful to him for that. But of course, you don't get promoted based on activities like that. You get promotion to professor at Imperial based on your science. And Paul has really done his scientific ancestors proud as well by becoming a world-leading authority in silicon chemistry in his own right. So we're looking forward to hearing about it. And without further ado, I'll invite Paul to give his inaugural lecture entitled, In My Element, Adventures in Silicon Chemistry. So, Professor Paul Lickiss.
Thank you, Alan, for the kind words, and thank you for so many people coming. I was saying to people earlier on, it's very strange to see such a variety of people from your background and people who've come a long way. So Karen has flown in from Switzerland, people from Scotland, from the Lake District, and all over the place, as well as within the department and within the college more widely. Of course, this didn't happen without me I should give some thanks to how we've got to this stage right now. Whether there are any thanks at the end remains to be seen from Alan. But I must thank James Romero for making the invitation to give the lecture in the first place from College Communications, for Maria Tortelli for getting all the cupcakes organised, which I hope you've enjoyed, for Luke and for Ben from my group, and for Matthew and various other people who've helped with the preparation of slides. And you might imagine there's some chemistry going to happen from what we can see at the front. And my old friend Richard here is going to do some chemistry for us later on. So thank you very much for giving up your time and coming here to celebrate today. Just occurs to me, several people have said, I like your tie, which is nice. But I was also, it only just occurred to me, various people said, you can't. I've had differing opinions. There are people who have said to me, well, surely you're going to give your lecture in your red jumper. How can you not give a lecture in a red jumper? On the other hand, there have been a similar number of people saying, you must not give your lecture in a jumper. You better wear a tie and a jacket. So if it gets cold later, I'll perhaps pop this on. Anyway, we have a title up here, and as Alan said, the vast majority of the chemical career so far that I've enjoyed has been in the chemistry of silicon compounds. And what I want to do is to split the talk really into two halves. The first is to introduce you, if you don't already know it, silicon chemistry. And the second is, you will all know me to some extent, a little bit about me and how I've got to where I am today. So, all inorganic chemists start with the periodic table, and I hope you all recognize that, even if you're not a chemist. And I've chosen this one particularly, as you will see, because Oxford Labs, of course, have highlighted in their periodic table the most important element anyway. And for those of you who are less familiar with where it is, it's in the sort of top right-hand corner here. And an important feature is that it's just below carbon in the periodic table. And we're all perhaps more familiar with the chemistry of carbon compounds, organic chemistry. Some of what I want to do today is look at comparisons between silicon and carbon. So remember where that is in the periodic table, just below carbon. Of course, if you are a silicon chemist, and there are a few in the audience, the periodic table looks completely different, and it looks like this. Okay, now I guess some of you have seen this before. Certainly those of you who spent a lot of time in my office have seen this before. And here, I know it's not very clear on this view, that is the silicon there in the center. So this is hydrogen, and this spirals outwards, and is actually a very good periodic table. There's nothing wrong with it. It is periodic. And if we look in more detail here, we can see silicon here. I realize this is from an original. This is from Dow Corning, from John Hyde. And this is a very creased up old original. And it shows that silicon connects to all sorts of different atoms in the periodic table. And we'll see some of that chemistry as we go through. So here's hydrogen and helium, and we cycle round. And you can see here that we've got silicon and group 4, and also group 14. So it actually makes a little bit more sense than some of the traditional look of the periodic table. So that's where it is in the periodic table. What do we know about silicon? If I say to you all, what's the one thing you think of when you come across the word silicon? Does anyone want to say something? Silicon, sand, chips. Silicon Valley, okay, we've all come across Silicon Valley. And we've all come across, I don't know who it was that said chips, but silicon chips are part of all our lives now. And what you don't often see is this sort of arrangement here, where you see this round disc here is a wafer of silicon before it has been sliced up and had all the individual chips put on it. And you don't see these very often. I've got a few mounted on cards, so you can see what these look like before they actually end up in your computer. And there is one that is just a single disc, and these are, you can actually pull them out. They won't fall off the piece of paper. You'll see the mirror finish on these and the detail of the chips on the silicon. So this is the element silicon, which is largely, I don't usually deal in lumps of silicon, but we'll see more about that later. Here is a lump of silicon. This is what it looks like, and it's on that diagonal in the periodic table where things are sort of not quite metals, and they're not quite non-metals. They have some properties, so you can see that this, you might well say, well, that looks like a lump of metal. It's shiny, it's silver, you know, it sort of has some metallic appearance, but it's a semiconductor rather than a good conductor, which is why it's of use in the electronics industry. So the wafers that are making their way around are made by this tall cylinder here, about as big as this person. This is a single crystal of silicon. And this is grown by something called the Czochralski method, and the wafers, those round wafers that are going round, are slices across here. Okay, thousands of them from a crystal this size. So that is where the silicon for the chips industry comes from. And I've got some lumps of silicon for you to look at more closely, one particular big lump here. And at the end, as well as having what I hope is your silicone cupcake, there'll be pieces of silicon for everyone at the end, of anyone who wants one to take away a chunk of silicon when you leave at the back. And I'll say again a bit more about that later. So this is the element silicon. Somebody said sand. So this is silicon dioxide. We're all familiar with carbon dioxide, which is a gas. Silicon dioxide is sand. Silica is another word that's usually associated with this. And you can see this one doesn't have any web attribution to it. That's because this is a holiday snap, and you can see my family there. My wife and my son sitting down here in the front. You can see, gives you some idea of the scale of this beach. It is huge. And somebody said to me who saw this slide earlier in the week, oh, is this Morocco or somewhere? And it's the Isle of Lewis in Scotland in the Western Isles. So I can recommend that if you want a nice beach. So this is silicon dioxide, and this is the material that is a large component of glass. And we'll see more about that later as well. So that's another word that came up when we were thinking about what about silica, or silicon. Something that people didn't say, but which is something that has become one of those sort of questions that occurs now and again in science fiction in particular. Could you have silicon-based life? Now, this isn't new. As you can see here, H.G. Wells said, one is startled towards fantastic imaginings by such a suggestion, visions of silicon aluminium organisms. Why not silicon aluminium men at once? I don't know what about women, but wandering through an atmosphere of gaseous sulfur, let us say, by the shores of a sea of liquid iron, some 1,000 degrees or so above the temperature of a blast furnace. Well, H.G. Wells had a wonderful imagination, and we've never found anything like that as far as I know. But much more recently, of course, we have the science fiction field of writing and films, and some of you may recall that there was a thing called the Horta from Star Trek, and these, I'm afraid these are rather indistinct, but these sort of balls here are supposed to be the eggs of the Horta, which are made of solid silicon, apparently. So is there life as we know it based on silicon? We'll see in a minute. So I mentioned silica and silicon dioxide a moment ago, and there's a couple of things here. I often bring a real milk bottle with some real stinging nettles in it to schools events and pass it round very gingerly and say, what's the connection? And the connection here is that the glass, of course, as I just said, is mainly silicon dioxide, silica sand formed into glass. The connection with the nettle, as I guess most of us here have been stung at one point or another in our lives by one of these sharp spines on the nettle leaf or the nettle stalk. And these are pure silica, the same material as makes up the glass bottle. These are silicon dioxide. The plant extracts silicic acid from the ground and then builds a real structure to help protect itself from herbivores and other problems that it might encounter. So these two things are linked by silicon chemistry. What about other life? And if we're going to ask the question, is there silicon-based life, we might look at it from a slightly different perspective. So these things here, this crab is looking at rather intently. If you look closely, you can see that there's actually another crab inside there. These things here are called glass sponges, or have the common name the Venus flower basket. And so this is a marine mammal, a marine animal that lives attached to the bottom of the sea in various parts of the world. And these are quite large. It's not easy from that picture to see quite how large they are and how spectacular they are, but I do have one here. Several of these things I'm going to pass around are rather delicate, particularly this one. So if it does break, don't worry, but I think they're in cases robust enough to survive. So the thing that's going round there is one of these, and it's about, as you probably saw there before I handed it to Richard, it's about 8 or 9 inches long. And when you look at it carefully, you will see that it is a silica. So this is, again, silicon dioxide. This is a macroscopic silica skeleton. So we might ask the question, is the silicon-based life not as we know it, as they say in the films, based on biological carbon chemistry, but this organism is largely comprised of silica. It has a silica skeleton. It can't exist without its silica. And so in one sense, we might say this is a silicon-based life form because it can't do without it, and this is not some minor trace component. Its entire skeleton is made of silicon dioxide, and I think you'll find it fascinating to see the complexity of the structure that the animal manages to build up. So this is macroscopic, and these are relatively unusual organisms. Far more common are things called diatoms, which you may well have come across. These are microscopic marine and freshwater organisms, and these fantastic shapes are all, again, silicon dioxide, silica skeletons. So again, the animal has abstracted silicic acid from its aqueous environment at low concentration and has built up a complicated skeleton for itself. So again, one might say in one sense that this is a silicon-based life form. Another word I think I heard when I asked for comments about the word silicon was silicone. I think everyone's heard of silicones, and one of the things I want to do today is to try and distinguish, for the non-chemists particularly, the difference between silicon and silicone. And I can see one or two people smiling at the front because the chemists know exactly what the difference is, and in the media, and many people misunderstand these two words, and they are fundamentally different. So we've seen some pictures of silicon, and these things called silicones are long polymers of that general formula, and we'll come back to the formula later on. And these things called silicones are everywhere. They're sold by Dow Corning, and I believe other silicones are available. Yes, we have this. So Richard here in the front row works for Dow Corning, and you may well have used bath sealant. You may have used mastic for sticking all sorts of things to all sorts of other things. If you use a deodorant or a hairspray or all sorts of personal care products, they almost all contain silicone, such that there is some marketing nowadays where you see some materials that actually say on the front, does not contain silicone, based on the assumption that pretty much everything does, and if you don't think it's a good idea, here's one that doesn't. So they are everywhere, and that can be a problem in analysing them. So why are these things useful? They are robust. You can heat them up, you can add lots of different chemicals to them, and they are stable towards water and all sorts of other things. If you've got a fish tank at home, it's probably stuck together with beads of silicone sealant. They're good insulators. Non-stick is a useful feature. Anti-foaming, I believe the first major use of anti-foaming silicones was in pickle brine, and then just after that in anti-foaming in the beer industry, where you don't want all your vessels full of foam but full of liquid instead. Part of the chemically robust side of things is that they are resistant to oxidation in the air as well, and they also repel water, and we'll see why that is in a moment. So these things came to the UK in the early 1950s, and this is the earliest advertising I can find for the silicones in the UK. 1953, and they came from the States. And it mentions, you probably can't see here, that Midland Silicones, a precursor of the Dow Corning Corporation now. I think that's true to say. So silicones are also something, a word that we might associate with the term silicon as well. So why are they important, and how are they different to silicon? So you all saw some silicon, it's going round, it's a nice shiny metal-like thing. I hope many of you might have got a cupcake case, and I think if you all feel this and scrunch it up and it comes back to its shape, the one thing this isn't is grey, shiny, brittle, hard, metallic, or any of those other things that we associate with the lumps of silicon going round, okay? The shiny grey stuff is silicon. This stuff is silicone. It's a polymer of carbon, oxygen, silicon, and hydrogen. And I'll pass a few things round. I guess you've all got one of these things round. But you'll realise that you can make things from them. Some of the silicones are relatively low molecular weight. I can find it here. Some of them are liquids, fluids. Okay, I think perhaps I won't pass this one round. It's a runny liquid. You can probably see it there. Some of the things, though, if you make a higher polymer and cross-link it, you can make an article. So this is silicone tubing. We have a baby's dummy. The more modern baby's dummies are almost always made out of silicone rather than natural rubber. And a trinket from Dow Corning. Not quite sure what it's supposed to be. An insulator, I think. And if I pass these round, you'll feel that they have a characteristic feel to them. They are flexible. They are soft. They go back to where they came from if you deform them. And they have this slightly silky, smooth feel to them. And that's what you get when you put it on your skin, if you have a deodorant or a hairspray or something like that. That silky feel is due to some of the features, all the hydrocarbon substituents. These Me things here, these are methyl groups, CH3s, and they are hydrocarbons. So that's why they feel a little bit like wax or a little oily. So for those of you who thought, actually, this isn't too bad, I've almost got some of this. There will be some real chemistry coming up, so hold on to your hats. I will try and explain as best I can, and I'll bring out what I hope are the salient features from the slides that look rather scary. So I mentioned at the beginning that silicon is one lower than carbon in the periodic table and in the same group. And that suggests that we should have some similar chemistry in the same group of the periodic table. So let's look at some basic properties. So the first thing I've put, which many of you may never have heard of, is this thing called electronegativity. How positive or negative an element likes to be in rough terms. And you can see that the value for silicon is significantly smaller. This is a total scale only ranging up to 4. So this difference is quite large on a scale that only goes to 4. And what we can see here is that silicon likes to be more positive. The lower the number, the more positive it likes to be. And we'll see some aspects of that coming up in the chemistry shortly. How big is a silicon? A silicon, these are picometers here. That's 10 to the minus 12 of a meter. There are more of these here than there are there. Silicon is bigger than carbon. And that means that if you have its bond length, E here is either silicon or carbon. The bond length to itself, 233 picometers, is significantly longer than 154 picometers. If you can't think in picometers, just think meters. 233 meters is a lot more than 154 meters. Okay, it's longer, but on a microscopic scale. The bond strength, because it's longer, it tends to be weaker, and you can see the bond to itself is weaker here. But, importantly, this bond, either carbon to oxygen or silicon to oxygen in kilojoules per mole, you can see this number is significantly larger than the carbon number. So this suggests that silicon likes oxygen. And we only have to look around the world to know that that is true. 4 out of 5 of the atoms available to us in the Earth's crust are silicon or oxygen, and they are very often connected to each other in this stuff we call sand, or silica, or silicate rocks. And this is what drives the formation of them. This is an exceptionally strong bond. Not only is it strong compared to this one, it's strong compared to the vast majority of other chemical bonds. And this drives the structure, really, of the Earth. This is what the silicate rocks are made of. Another thing at the bottom is multiple bonding. So for those of you who know your carbon chemistry, and there are many of you here, of course, know far more about organic chemistry than I do, this is a so-called double bond, an alkene, and this is formed because the p-type orbitals, these things here, overlap reasonably well with each other on adjacent carbons. The silicon-silicon distance is somewhat longer, and there is weaker overlap. So to cut a long story short, the general thing we learn from this is that silicon doesn't really like to form double bonds, and it forms single bonds preferentially. And we'll see more about that as we go through. So this one looks even worse from the point of view of chemistry. It wasn't just a little table. This one's got some real bonds and things in it for the non-chemist. So what can you take home from this? Well, I just said that silicon doesn't like to form these things called multiple bonds, where there are two bonds to the silicon. It really doesn't like to do this, and if you try to do it, it forms something with single bonds instead. It oligomerizes into a trimer here, or it dimerizes, usually in a head-to-tail fashion here, or it forms a cyclic ring here. If you try and stabilize it by something called aromaticity, if you make a silyl aromatic, it dimerizes to something like this. And if you have a silane, by analogy to an alkane, it reacts readily with acid and base to form this thing here called a silanol that we'll see more of. By comparison, all the carbon analogues here, carbonyls, alkenes, aromatics, alkanes, these are all generally stable to self-reaction under normal conditions. They all react under some conditions, but you can isolate all these things at the bottom easily, and the whole of organic chemistry would disappear if you suddenly took away all these groups here. But they are, in silicon chemistry, they're really quite rare. And so a lot of what's happened in silicon chemistry in the last few years has perverse people like myself have been trying to make silicon do these things that carbon normally does, and to see what effect that has. So there's a strong driver here to try and understand silicon with respect to carbon chemistry. So, a change, okay? Early problems with silicon. So I started silicon chemistry. I've introduced you to silicon and some silicon compounds. What I want to do now is to do a bit of introduction to me and how I got to be standing in front of you today. So here we are on the beach in Hastings. Doesn't quite give away how old I am, but you can guess roughly from that. And if you spend your morning working with silicon compounds, building sandcastles, you end up with it in your shoes, and it's a bit of a problem. And so here we are emptying our shoes of silicon compounds after a hard morning on the beach. So we start off with some silicon compounds there. How did I get to where I am today? So this is, I think this is a lovely picture for those of you who like attractive pictures in prospectuses, for those who are interested in advertising universities. This is a lovely picture of Sussex University in the 1970s, and some of us were there at the time. This is the chemistry department, or as it was called then, molecular sciences. In the background, this very long, thin building that continued behind the other one here. And the lab that I worked in was on the top floor, just about there. The infamous Lab 13. I'll tell you why it was infamous in a moment. But I want to come to some people now who have been strong influences in my chemical journey, shall we call it. And there are two people here, one of whom I guess the vast majority have at least heard of, if not know personally. The other one, I think many of you will not know. The one that is famous is this chap on the right, Harry Kroto, who won the Nobel Prize in 1996 for the discovery of carbon-60, Buckminster fullerene, and all that sort of thing, nanotubes and all that sort of thing. And Harry jointly won the Nobel Prize for that exciting discovery and further work. So you may say, well, what's Harry Kroto got to do with me? So Harry Kroto was the person who did my, in those days, UCA interviews, in nowadays, your UCAS interview. And Harry read my UCA form, and after a few moments he said, I see you're interested in lasers, and you've built one at school for your O-levels. So I said, yes. And he said, well, never mind this interview. You come to my lab, I'll show you some lasers. And so that was the end of the interview. We went to Harry's lab, and we shot around all sorts of nice things in the dark. And remember, in the 1970s, lasers were rather less common than they are now. This was exciting stuff. And so I left Sussex University in, I think, February of '77, thinking, well, this is a great place. I've got to come to Sussex. And so I did. So Harry was quite influential. Of course, later he became a colleague, and I got to know him well. The other person is Dave Walton, who worked a lot with Harry. This is a picture taken in Dave's office. And Dave Walton was my personal tutor while at Sussex, and also was a silicon chemist. And so was actually very influential, not only as an undergraduate personal tutor, but after that, his group shared the same laboratory that I worked in. And so I saw a lot of him, and he was always a wise and caring voice. And I know some of you in the audience know Dave quite well. I see Bill here knew Dave Walton well. And he was always a caring and sane voice. Sometimes when the lab got a bit fraught, I knew I could always pop in and have a word with my friendly old personal tutor. Sadly, neither of these two are with us anymore, and Harry died only very recently. Perhaps even more influential, of course, you've got to get to Sussex to start with, but even more influential, I think, is Professor Colin Eborn here, who was my PhD, or in Sussex, it's a DPhil, my DPhil tutor, or supervisor, should I say. So Colin, there's a number of people here knew Colin, and I think it's true to say one hears occasionally bandied around the word a scholar and a gentleman, sometimes not necessarily entirely complimentary, but I think for those of you who are in the front who knew Colin well, he was one of the old school, a scholar and a gentleman, a very kind supervisor, a great scientist, and somebody who helped me very significantly, not just through my PhD, but in the years following that. So I have a lot to owe all these three people at Sussex. So, spot the person with the hair now. This is the only picture I could find of me in some sort of action there. I'm glad to say I'm wearing safety specs and a lab coat. I think there are several members of the current safety department here, so I hope you're satisfied, although I must say that the state of the bench is, I would not be happy if my current students were in that state, but that was the way I worked at the time. And as I said, this is in what was known as the infamous Lab 13 for a very unfortunate reason, and that is that there was the other end, so my bench was at one end of the lab, and it was a big laboratory, and at the other end of the laboratory, one of Dave Walton's students, Dave, who you just saw, had a very severe explosion in the mid-1980s, and this was one of the driving forces for something that we all know and take for granted now in the chemical world, COSH. So everyone nowadays, we live by COSH, the control of substances hazardous to health. Okay, so this is pre-COSH, and the explosion at the other end of the lab was one of the drivers for that, because it led to a big court case, which I was called as a witness, so that's why I say the infamous Lab 13. It was a very serious injury, and a student nearly died. So that's me in the lab. Now we have to get back to some chemistry, and some of you are very familiar with these reactions, and I apologize for those of you who've seen it all before, but many of you will not be familiar with these. So one of the things I said at the beginning of the comparisons is that silicon, silicon is much more electropositive, and so you would think would form these things called cations easily compared to carbocations. In the carbon case, these are fairly well known, and you can isolate them. In the silicon case, they are extremely reactive, react with almost anything, and making a 3-coordinate silicon cation has turned out to be one of the big challenges in main group chemistry. So I want to show you something of my PhD studies and work after that in just a couple of slides, resulting in about 50 publications. So fortunately, I'm not going to go through all 50. There are a couple of reviews here at the bottom if you're interested in that chemistry. So you can do a Wurtz-type coupling reaction here to get this unusual alkane. This CH is quite acidic because of the alpha silyl groups, and you can metallate it with methyl lithium to form this lithium reagent, which, as you can imagine, you can do metathesis reactions with this, with almost anything, any halide in the periodic table. So there's some silicon halides here, and to give you some idea of the effect of this bulky group, so steric hindrance, bulk on 3 dimensions. Steric are 3-dimensional space filling. So these are silicons with a very, very bulky substituent on them. So what does this do? This makes the chemistry of silicon rather more like carbon, because a lot of the mechanisms of silicon chemistry cannot occur if you protect this reactive center with a huge, great group around here, and I'll show you a picture of that in a moment. So for the chemists among you, you will realize that if the 3 R groups here are chlorine, this is a trichlorosilane, and chlorosilanes are well known for being very moisture sensitive. Okay, and there's a lot of chemistry of that sort coming up. This one is water stable. Not only is it water stable, you can reflux it in methanol literally for a week, and it does nothing. This stuff is like a brick, and yet it is a trichlorosilane. There's no funny business about rings or aromaticity or anything else. It is purely that there is a great big blob of hydrocarbon around here that prevents the reactivity that you might expect. Perhaps even more spectacular for the organometallic chemists here is this dialkyl zinc here. Now, for those of you who don't know, this type of reagent here, dialkyl zincs, are normally pyrophoric in the atmosphere. That means if you just take them out in the atmosphere, they go up in flames. These are highly reactive species, yet this one can be steam distilled. You can heat it in water, you can do what you like to it. It has no chemistry. In fact, it's gone so far, it's not very useful at all because you can't do anything with it. And the reason for that is, just as I said a moment ago, is what is called steric protection. So here is our zinc in the middle, which is this sort of pinky magenta sort of atom in the middle. The silicons are the blue ones, the carbons are black, and the white are the hydrogens in these peripheral groups here. And you can see that even when a student and I sat down and looked at this carefully, even though we arranged the view the best we could, this was the best view of the silicon atom, the zinc atom in the middle that we could find. And the reactive part of this molecule, the reason for its reactivity, is this carbon to zinc bond here. And as you can see, you can't really even see the reactive part, the carbon-zinc bonds. And so molecules that might react with this, such as moisture, water in the air, or oxygen, they just can't get in there to do any chemistry. And so this idea of protecting things with a great big bag of hydrocarbon around the periphery means that the chemistry is significantly different to that you'd normally expect. So, how did we use this to approach the cation question? Here's some even more scary chemistry. So the important things to note, we have our bulky group here, and the reaction that we're going to do, this hydrogen here, this is on a silicon which is positive, so this is hydridic. And we're going to remove it with this cation here, so this is like an anion H, this is a cation, and so this is going to form triphenyl methane here. And the idea turned out to be an unsuccessful attempt. The idea was to take this hydrogen off, and then we'd end up with a cation with 3 things attached. which was the aim of all silicon chemists for 50 years. So unfortunately, this didn't work. Silicon really doesn't want to be 3-coordinate cation. And what happens is it forms this. So this silicon here and this one here now has 1, 2 bonds to it, and 2 of these other methyl things attached to it. So they are both 4-coordinate, but what we have is a bridging phenyl group. So this is crystallographically determined. Here's the crystal structure of the cation. There's also a great big anion here. This is the crystal structure of the cation. You can see a slightly puckered 4-membered ring there and a bridging phenyl. So this is an extraordinarily unusual situation for carbon and silicon to find themselves. This is reminiscent of group 13 chemistry. This is the sort of thing that happens if you might have an aluminium or a boron or something like that. It does not happen in group 14 chemistry where we find carbon and silicon. We did a similar reaction with this compound here where we had 3 H's here. We were planning to take 1 off and leave a 3-coordinate silicon cation. It didn't do it. Again, it formed 4-coordinate silicon here with a bridging hydride in this case. And again, very unusual, the sort of thing you would expect with group 13 chemistry. Sorry, I'm rather talking to the experienced chemists here, but this is extremely unusual. Take it from me. I think that's true to say for the chemists. That is not what you expect to find. Perhaps even for the chemists, this one has something that you may not have spotted. I think all the chemists are sort of sitting, yeah, okay, I can see that. What you may not have noticed is that the starting material here has 3 times 3 of these methyl groups. What you see in the product is that there are 6 here, 7, 8, 9, 10. So we started with 9, and the product has 10. Okay? So I don't know how many of the chemists would admit to not spotting that it had gained a methyl group, but there's rather a more subtle question. And what happens in these compounds is not only do the groups bridge around, they sort of go around in a merry-go-round, everything exchanges. They do that both within the molecules, so-called intramolecularly, but they also do it intermolecularly. So this thing has picked up one of these little Me groups, a CH3, a methyl, from another molecule. Okay, so there's inter and intramolecular exchange. Again, very unusual. So I could tell you lots more, 50 papers worth or so of this. Pindili Masangani was the person who got the crystal structure of both, or crystallized both this cation and that cation. I haven't got the picture of that here. And some of the people in the audience did this work. So I've got one slide on a year in Toronto, and this addresses this double bond question. I said earlier on that silicon really doesn't like to do this, and it's because of this poor overlap of orbitals. And what we find is that to stabilize something like this, so that you can isolate it, again, you need this idea of steric protection. You need a great big ball of something inert around about the reactive center. So in this case, the reactive bit is this silicon carbon here. This R group here, I should have drawn this out. This is adamantile. This is a great big complicated organic substituent. So R is big. These trimethyl things are big as well. And if you have a large R group, then this thing is actually stable. And when I say stable, it's stable towards reaction with itself. So it doesn't do that dimerization reaction we saw. But I've tried this. If you take a little bit out of the Schlenk tube on a spatula and wave it around in the air, it goes poof in smoke. Okay, so it's very reactive towards small molecules like water and oxygen. So my part in this was to remove one of these trimethyl silyl groups, because this is fine, but you don't have much chemistry here, is to make a different R group and look at whether you could stabilize these with a little bit more in variety in the way of the backbone of the structure. And indeed you could. And we published a number of papers on this. So I also tackled some of the early work on the double bond question while I was a postdoc fellow with Adrian Brooke in Toronto. However, I came back, as Alan said at the beginning, I came back from Toronto back to Sussex as a Royal Society research fellow, and started to do a lot of work on these things called silanols that I mentioned a few minutes ago. So another comparison of carbon and silicon chemistry. Here's something called an aldehyde or a ketone, a carbonyl group, and double bond silicon that I said was stable. And towards water, the equilibrium here lies very much this side. So things like ketones and esters and carboxylic acids and aldehydes are generally quite stable towards moisture. On the other hand, if you were to prepare one of these things, and these are extraordinarily difficult to make, they react rapidly with water to give this thing here called a silane diol. And we're going to look a lot of the chemistry at these in a few moments. Don't worry if you're thinking there's going to be another 10 slides like this. There aren't too many of these coming. So why are these things called diols important? They are important because if you get several of them together, for example, a pair of them here, they lose a molecule of water, and you form this SiO-Si link. Okay, we have SiO, lose water, and form this thing in the middle here, and this is called a siloxane. So this is SiO-Si, the siloxane linkage. And this is the thing that holds rocks together. This is the thing that holds sand together, and concrete, and glass, and everything else. The world is largely held together by this little group of 3 atoms here, polymerized over a large scale. Okay? And the silicones that I mentioned, or we saw some examples earlier on, you can imagine that we've still got an OH here and we've still got an OH here like these, but these get together, lose another water, and these little molecules form bigger, bigger, bigger long chains, and that's where the silicones come from, and that's why this thing called a diol is very important. You can get small cyclics, you can get long chains, and you can do lots of chemistry with these. So it's probably about time that I stopped talking for a moment and we had some chemistry. And I'm very pleased to say that Dr. Richard Taylor here from the Dow Corning Corporation in Wales has, so he's an old friend of some of us, and new to many of you. So Richard and I were undergraduates together. We went to university together in 1977, and we've known each other ever since, and we've both been silicon chemists ever since. And Richard went into the industrial side of things, and I've stayed in academia. Richard has sponsored all sorts of PhD students and projects and things over the years, so I'm very pleased that he was able to come today, and even more pleased that he's going to, instead of me having to do the demonstrations, if they go wrong, we can blame Richard. What I want to demonstrate with these is 2 reactions. This is the first one, the silanol polymerization. Now, this is something that many, many of you might have done, probably in your bathroom. Okay, this is the reaction that gives you a silicone sealant. When the stuff comes out of the tube, it's relatively, I mean, it's not runny, but it's relatively mobile. Okay, you can smear it around. In fact, it ends up smeared in more places than you want if you've worked with it. You can smear it around, and then after some hours or perhaps overnight, it does 2 things. It smells a bit of vinegar, and it forms a nice bead of silicon or a sealant, an adhesive to glass or whatever. So what we've got here is the monomer here is this long chain thing, and you can see it's got the OHs on the end. To make it a bit quicker, so you can see it's a mobile liquid, looks like water. So as we haven't got overnight to see this happen, we've got a nice catalyst. So this is a phosphazine catalyst here, this thing represented by P, and Richard's going to add that, not very much, as you can see, from a tiny syringe, and screw the lid on and give it a bit of a shake. And what we should do is polymerize here. And you can see already, those of you at the front, it's going a bit milky. I think we'll be able to pass this round. And in a few minutes, what I'd like for this one to do, if we could pass this back and then pass it back to the front, we'll see what it looks like in a few minutes' time. So it started to go milky. So this is the polymerization reaction. Please don't drop this on the floor. Don't open it. Don't open it, yes. It's not toxic. It wouldn't harm you if you did drop it on the floor. It would be like getting silicone bath sealant on yourself. You wouldn't be able to get it out of your clothes, but it's not dangerous in any way. So please don't drop it, but it's not a problem. It's not toxic. No, the greasy silicone look is not good. So what's happening is that we're going from a small molecule with low viscosity to a great big molecule with a high viscosity as this polymerization takes place. So while that's going round, and it can come back to the front in a few minutes, we have another one, rather different chemistry in this case, and this relies on a different reaction. So we have, in this case, we have two different silicon precursors. One of these has this SiH, and we saw at the beginning, unlike CH, SiH is quite reactive. So we have an SiH compound and we have an SR vinyl compound. So we have an unsaturated carbon compound here. And what we're going to do is to add the SiH here across this multiple bond, and we're going to form this CH2-CH2 link here. So this is catalyzed by platinum, and I think Richard's got a little bit of a platinum complex, and for those of you who are into your coordination chemistry, you can see this is the so-called Karstad catalyst at the bottom, complicated vinyl siloxane catalyst. Okay, Richard. So again, this was a runny lot of liquids, and Richard is mixing the catalyst, this platinum catalyst, a tiny drop of it, into these two runny liquids. And what Richard's going to do, we're going to see whether the polymerization is taking place, and the rate of it is, you'll see why why this one's not going to go round. And Richard's going to, with great finesse, I hope, Richard's going to pour it, and as it polymerizes, we might, yes, it's polymerized on the way down. Okay, so I don't know how long that took, how long I was talking for there. 10 seconds, 20 seconds maybe at the outside. So you can tell Richard's done this before in front of an audience, can't you? This one has polymerized much more quickly. And this is the sort of material, and I have some of this here as well, some real life material. These things have lots of applications. This is the material that we've all got lots of at home, of a coating, a silicone release coating. And again, this is just a stamp. It's Richard's stamp, so please don't. Please, it should come back to the front. But if you feel, I mean, normally what we do is we tear off whatever is on the coating and we throw the coating away. But if you feel that, again, you'll feel it has that slightly waxy, smooth feel that the silicone materials that we saw earlier on have. So that's where this type of polymerization, another thing that relies on this SiO polymer, stable polymer material. I think we ought to give Richard a round of applause for that. I think timing it just right is you need a bit of practice for that one. So thank you, Richard. So let's look at these silanols in a little bit more detail. How might you make them? They're quite easy to make, and you take a chlorosilane often or an alkoxysilane with R is these various groups on here, and you hydrolyze it. You add some water, and you get a diol and hydrochloric acid or something like that. And the substituents are here can be big, small, alkyl, aryl, all sorts of things. So these are well known. You might well say, well, what was your contribution? Why was this of any interest if they're easy to make and they're well known? So when I started in this field, there were a number of these known, and they were usually in the books you saw and the reactions things that you saw, they were in curly brackets as sort of something reactive on the way to the silicone, on the way to the interesting bit. And what we did was form nice synthetic routes where it didn't go off and do something else, where you could isolate them. And one of the things we did was to look at very mild methods. So this is this rather strange-looking molecule. It's dimethyl dioxirane, which oxidizes an SiH to a silanol. And we'll see that structure in a moment. These silanols are also found on silica surfaces. And if you want the really big picture of what holds the world together, all the silicate rocks are held together by SiO bonds. How does the inorganic world of silicate rocks speak to the organic world of aqueous solution, largely. The organic world is floating around in seas and rivers and soils and things. So the two talk to each other via something called hydrogen bonding. So these silanols are on the surface, and they interact with water and other things there. So it's really these things that hold the world together and get the inorganic world to talk to the organic world. I should say there's various names appearing here of people who worked in that particular area. So here's some pictures. The hydrogen bonds are the yellow ones, and these are compounds I made myself, which is why there isn't any other author there. And you can see they form a variety of things. These are two chains, but different types of chain. So these are these diols. There are two of them. And the third one is a triol. So these are very difficult to make unless you have, again, one of these very bulky groups here. And you can see the structure there is really very attractive and interesting. This is 6 of these molecules hydrogen bonded together to form an 18 oxygen polyhedron in the middle. So here is one of these trials again, and we start to get to some chemistry that not only looks a bit complicated, but you can't say it either. Silsesquioxanes. So everyone in my group knows how to say that. So these are actually polyhedral oligomeric silsesquioxanes, and they are fortunately usually abbreviated to POS, which I haven't put here. And they have all sorts of structures, and the ones that we've been particularly interested in are the ones that are full polyhedra. You can get ladders, you can get a mess, you can get something that's nearly a polyhedron, and a full polyhedron here. And we've done a lot of work in this area, culminating in a very extensive review. And some of the people, actually not some of the people, I think only one of the David Cordes is in the audience this afternoon. Whoops, 2 at once. So, why have I brought them up? Apart from their very interesting chemistry, something I didn't want to skip over because it's been subject to very long-standing and fruitful interaction with groups headed by David Rankin in Edinburgh, Sarah Masters, who's now in New Zealand, and Derek Wan, who's now in York. Derek's somewhere here in the audience. Sarah tells me she's getting up especially early in New Zealand. So Sarah, if you're out there somewhere, hello from London. Derek's here, Karen's here, and various other people you know are here. David Rankin is not here, but he's not far away. So he's at his gold medal winning Chelsea garden, maybe 2 miles from here. He's an alpine plant expert, and is now busy winning gold medals at Chelsea instead of doing chemistry. But this is a very fruitful area, and this is very difficult to do, this chemistry. So this is electron diffraction. So most of the chemists are very familiar with X-ray diffraction, where you take a crystal, you shoot X-rays at it, and you determine a molecular structure from its diffraction pattern. That's fine if you've got a nice crystal, and it's fine if you want to know what things look like in the solid state. If you want to know what it looks like in the gaseous phase, you need to do something else because you haven't got a crystal, and electron diffraction is used. And I'm not going to attempt to describe that to you here, but it's a much more difficult technique than crystallography. And here are 2 structures of these polyhedral things here. So these 2 particular ones were done by the Edinburgh group. Others that we've done have been done by a group in Russia as well. So I'm pleased to see that Derek is in the audience today. So these are very, very popular compounds. And you might say, well, why do you want to know what it's like in the gas phase anyway when you've got the crystal structure? And the answer is that largely computational chemists tend to do their calculations, often, not always by any means, but tend to do their calculations on single molecules because it's relatively easy. And then they compare the structures with something from the solid state, the X-ray diffraction. And in the solid state, you've got a molecule next to a million other molecules, and they're all packed in some sort of lattice. And so they deform each other. And so if you're trying to compare the calculation of a single molecule effectively isolated on its own with a practical structural determination, they tend to be quite different, or they may be quite different. They may be the same, they may be quite different. Whereas here we have the structure determined free from other molecules in the gas phase, and we get very similar results between the calculated structure and the practically determined structure by electron diffraction. One more thing that we've done recently with Tom Welton and Patricia Hunt in this department is to look at these siloxanes, these SiO, Si things, the runny liquids that we saw at the beginning, that type of compound, as solvents to replace non-polar hydrocarbons or aromatic compounds like toluene or hexane, and to see whether they can be useful replacement solvents because they're relatively low toxicity and they're not very persistent in the environment. They are also available on a very large scale. So I've just got two reactions here. This summarizes a vast tract of work we've done, and one can take these reactions. In this case, we've got an oxidation, and in this case, this is an alkylation. You can do these reactions in these novel solvents and get very similar results to the aromatic solvent or the hydrocarbon solvent. And so there is great potential, I think, for these to replace some of the nastier traditional solvents. So the last major topic I want to tackle is something a bit more pictorial. We'll do away with most of the reactions, and you're maybe already thinking we could do with some wine, and there will be wine and nibbles afterwards when we go out. To look at porous solids, particularly things called metal organic frameworks. And these solids they have lots of holes in them that you can put things in. There might be big holes, there might be little holes, there might be regular in one arrangement or regular in another arrangement, different sizes, different shapes. So can you make these things on a molecular scale? And the answer is yes. And we've spent a lot of time in the last few years working with these. The area was popularized by Omar Yaghi in the States. And the idea is that if you have a molecule here with a hole in it, you can build this up into something, a material that has porosity that you can put something in, that you might catch something in, store something in, and do something useful. So what are these things like? They are very porous. They have very high surface areas. So 1 gram of these materials may have a surface area of 3, 4, 5,000 square meters per gram. Okay? So that's one little tiny gram with a surface area of 5,000 square meters or more. And so if you want to absorb something onto a surface, you want a lot of surface, and you can put a lot of surface into a small volume. So these are nice crystalline materials, and you can do other chemistry with them as well. So how might you use them? You might use them for storing gas molecules. You might use them for hydrogen. You might capture CO2. A current topic of interest is carbon capture, so CO2 capture. And you might also, as we're just starting to, we have Jane Mitchell here from the National Heart and Lung Institute. We've just started a project, Rob Davis and I also mentioned here with Jane, on looking at the putting drug molecules in here and using them for drug delivery in the body. So how do you make these things? You make them by taking a metal center. So these things are called metal organic frameworks. So you take a metal, you take an organic linker, this sort of little rectangle here, and you connect them together. You connect them together in 3 dimensions. So this reaction, this is a reaction, so it tends to be done in a solvent, and you end up with the pores, but of course they're filled with the solvent. They're not connected to the lattice, they are within the lattice pores. You can then pump on it or remove the solvent by some method, temperature or heat, and form a hole, and then you can catch something. In this case, little green blobs are hydrogen. So what variables have you got? Well, you can vary the metal center, you can vary the geometry. This thing here might be octahedral like this with 6 groups. It might be linear, it might be trigonal, it might be tetrahedral, it might be rather more complicated. So there's lots of different building blocks here, and you have lots of different ones of the blue linkers as well. So here's a linear one, here's a longer linear one. This is, you would attach the metal via these oxygens here. Here's a trigonal one, here's a tetrahedral one. Here's one based on nitrogen rather than oxygen. So there are thousands of these linkers, and the whole of the periodic table worth of elements to play with as the possible nodes. So this has become a popular area, but Rob Davis and I have been working to look at how we might apply, as you might guess, how you might apply silicon chemistry to this. And I've just got a couple of examples here. We've developed a general method by which you can take a simple aryl silane here, metallate carboxylate and form a carboxylic acid here. And in this case, we've got a tetrahedral, tetrafunctional silicon linker, potentially. And here we've gone to a different, we've put an extra group in the middle here. So it's the same chemistry, and we end up with this hexa acid on the end there. So we've done a lot of work with these, and I summarize it in just a couple of slides. The first one, I'm not sure how clear this is, the first one here is using this tetrahedral linker here, and you can treat that with, you can treat that with a variety of these metal centers. So these are all 2+ metal centers, first row transition metals, and you get a wide range of different structures, even though you're using the same linker with different metals. So these have different porosities, different surface areas, and different chemistry that one might carry out within them. I'm not going to go through all of this, but you can make a wide range of things from this. You can use metals that are not normally regarded as metal organic framework metals, main group light elements. You want light elements if you go for gas storage. You can form metal organic frameworks with vacant or naked sites where you might do other chemistry. And this area, we just saw this molecule here. So if you treat this, this is a very complicated linker. If you treat this with zinc 2+, you end up with this cubic-looking structure here. And this has, the reason I've chosen this one is here's the compound that we were just looking at. And this, the reason I've chosen this is it's very similar to the classic now metal organic framework 5 from Yagi's group. So these are, there's the little blue tetrahedra here are zinc coordination, the red ones are oxygen, and there's a little linker, organic linker here, and this is a big space in the middle. That's what the golden sphere is to represent. So our one is similar here. It's got a low density, so this has lots of metal in it, but it has a density much less than 1. It's not what you would expect. And so you can put things inside this, and this one, our one, with the complicated linker, has only half as many zinc atoms, and we believe that this is an area that may well have a lot of fruitful research in the future, where we look at metal organic frameworks where the complexity of the linker means that you don't have to put as much metal in. So I hope that's something for the future. Here's a picture of it, a different looking picture. So you can see these pores here, these channels into the structure. And the last thing that I want to hand round, you've probably all heard of 3D printing. You can 3D print your molecular structure nowadays, and in collaboration with Henry Zepper and James Bannock in the chemistry department, 2 or 3 years ago, before this became something trendy to do, I think we were probably about the first people to really attempt this. You could take the crystallographic file that you get from your experiment and program a 3D printer to make a real structure. So I'll pass this round. You can see it has channels and holes in 3 dimensions. This one really is quite delicate. But I think it gives you a better picture than just showing you a 2-dimensional picture on the screen there. So, yes, Richard has passed back the... So I don't know how long that was. There's a few minutes of me speaking, and as you can see, it's polymerized very nicely to a nice gummy material compared to the runny liquid we had at the beginning. So that's worked very nicely, both the reactions. So most of you will know that I've spent more than the last 2 years responsible for quite a large-scale experiment out in White City, where what we've done is dig a large hole in the ground and fill it with many different varieties of silicon compound. many of which we've heard of already this afternoon. So what I want to show you is what you can do with silicon chemistry from a rather different perspective. And so silicon in the construction industry. So you can take a flat site and you can dig a big hole in it, which is the first thing that happened. And then after the snow has cleared, you can fill with concrete. You can put sand in. These are all silicon dioxide compounds, silicates. And then after a while, you will probably start to want to build larger structures, so more concrete goes in. The lift shafts will go in. That's the lift shaft on the left there, the lift shafts for the building. And then eventually, when you've got a bit more building there, you'll want to start putting some glazing in. So the glass is silicon compounds as well. What's the glass held into the windows or the frames with? It's held in with a silicone sealant, as Richard said, rather like this stuff here, a silicon mastic. And if you say mastic to the construction people, they all say, oh yes, silicone stuff. And that's what is gluing the glass in. So the glass is a silicon compound. What's holding it in is a silicon compound, and all the concrete walls and floors are silicon compounds as well. So that's a large-scale experiment we've been doing. And I don't know whether you can read that. So it says sand, concrete, glass. Can't read that myself, actually. Sealants, water repellency, tubing, adhesives, cables, solar cells on the roof. They're made of silicon, as we saw at the beginning. Electrical insulation, etc., etc. There's a lot of silicon chemistry in this building and in every other building. So it's nice to see quite a number of the design team, architects, engineers, all sorts of people that I spent the last 2 years working with here in the audience today. They've probably been transacting some work without causing me any trouble for a change today. So this, of course, was all done with lots of people. There were lots of names as we went through, and I put down there's collaborators here, as perhaps some people might be slightly surprised about. There were lots of collaborators named on the slides as we went through. But a lot of the people who do the day-to-day hard work are often not acknowledged. And as we've seen, there's been lots of crystallography. All those nice structures I showed you have been determined by crystallographers, not by me, and not by my students either. So I'd like to thank all these people. Some of them are in the audience, I think, or at least one of them's in the audience. These are the people who provide the data for the students to get the papers published. So I'd like to acknowledge them. NMR spectroscopy as well. This is often even less acknowledged. Rather few of them have their names on papers, but Alan Pidcock's an academic at Sussex, Tony Avent, published a number of papers with him and with John Ladd, and I think Dick and Pete are in the audience today and have done a vast amount for all the students that are currently working towards their PhDs in this department. Of course, the people who actually did all the work in my labs, this is the A to Z, literally. We've got Asri at the beginning here and Yannick at the end, the A to Z of people who actually did all the work in my lab. When you come up with a good idea, you go to your PhD student and say, will you have a go at that? That might work. And off they go. So I can't acknowledge all of them individually. I hope I haven't missed anyone. There are two highlighted here for different reasons. So Youssef Derouish was my first PhD student, and unfortunately he died many years ago. But I'm happy to say that Luc Delmas is my most recent PhD student, and he's helped me quite a lot with this presentation. So he's one for the future. Of course, there are lots of undergraduate project students, and they do a great deal of work as well that is often unsung. Of course, as well as the people who actually do the work, there's the people who actually fund the work. And there's a wide variety here that I'm not going to go through individually, but I was a Royal Society Research Fellow, so they are clearly very prominent in my background. Dow Corning, as I've already mentioned, has sponsored a lot of work. Polish Academy of Sciences here, rather a less obvious sponsor, has sponsored over many years exchange visits that have been proved to be very fruitful with various academies in Poland. I want to finish on a rather sadder note. This slide was going to go early on in my chronology, before Harry Croto and Dave Walton and all the others. So this is Dr. Colin Connolly. And Colin was probably the most instrumental person on setting me out in a scientific pathway at the beginning as a teenager. He was a real scientist, the first real scientist I ever met. And he took me to labs in London and showed me things and was generally enthusiastic. And I thought, I should be a scientist, this looks good. And so he has a very strong directing influence in the scientific sense early on in my career. I had hoped that he might be here today, but I'm sorry to say that he died on Tuesday. So he will be sorely missed, and a number of members, he's actually related to me within the family, the extended family, and some of his relatives are here today. So I put him right at the end because he deserves a special mention today. For the future, though, we have the current people in the group, not all of them. You can see this is just before one of our occasional bouncy castle group meetings. I'm even wearing my red jumper, you see. So these are the people who are the future. There's Luke on the end, who I've already mentioned. Bull is a PhD student. Jag here is final year undergraduate student. Gemma, who many of you know, is a postdoc. And Manon and Yingying are two MRev students. Some of the others are elsewhere and not in that picture. But I want to finish on that one because that's for the future. So again, I'd like to thank you for coming. I'd like to thank my parents and my friends and everybody else for the encouragement they've given over the years, my colleagues for being friendly and great people to work with, and thank you for your attention over a long and I hope not too complicated lecture. Thank you. I've got one more thing to say that I forgot. In the excitement of finishing, I forgot to mention one crucial thing, and I can see lots of you sitting there patiently with your cupcakes. So the cupcake case is made of silicone. Again, it's deformable. It's not a lump of silicon. But there are lumps of silicon for anybody who wants one available at the back as you go out. Oh, actually, they're in the buckets at the front. So if a couple of members of my group can come down, I don't know where Luke or Ben or Manon, do you want to come down and pick? You can take a piece of silicon to go in your silicone cupcake as you go out. Actually, there's plenty. If you want to take 2 or 3 bits, you can take 2 or 3 bits. Don't eat it. No, no. Sorry, Alan.
Right, well, after that, I don't want to hold you up from the informal celebrations with wine, etc. at the end, but you will all understand that a lecture of that quality deserves proper recognition. So I will keep you a couple of minutes to say how much I appreciated the lecture on your behalf, because the applause at the end was indicative. It's also, I'd like to thank Paul for giving me the opportunity to say a few nice things about it. I'll explain a little bit of that in a moment. And have remarkably similar backgrounds. We've never collaborated, and that's another story that I will mention very briefly. But I think just in that lecture, just to recap, starting with the periodic table, a kind of, for chemists, a very real thing, but a slightly abstract construct for the rest of you who don't deal with elements, and moving through the natural world, sponges and diatoms, actually talking about biological life forms. I thought his almost last slide of one of the moths looked like you'd reinvented the horter, actually. Oh. It looked remarkably like that sort of jelly-ish thing. But actually, the silicon turnover, biological silicon turnover on Earth is greater than the carbon turnover. Those diatoms really turn that silicon around. So Paul and I, both silicon chemists, I think with lots still left to do. Carbon and silicon comparison is a very important one, particularly more so for the inorganic chemist than the organic chemist. So Paul and I have got almost identical backgrounds. I ended up as a lecturer in organic chemistry and then a professor of organic chemistry, and Paul's inorganic. And yet we do more or less the same research. It shows that silicon can be taken however you wish it to be. Actually, organic chemists more often compare silicon with a proton, but that's about organic synthesis, a big proton. So, Paul, I loved some of the slides. When Paul was on the beach at Hastings, I was just starting as an undergraduate at the University of Sussex. So we are very similar in so many ways, apart from a 15-year gap. And I knew the same characters. And uncannily, Harry Croteau didn't interview me, but I played football with Harry and became a great friend of Harry's. And Dave Walton was not only my personal supervisor, he co-supervised my PhD with Colin Eborn. So talking about those characters and the tristle, I started off doing some of that work and got, I think, 2 papers, and Paul got 50, which I think tells its own story from that work anyway. And then moving through all those exciting things. I hope that the non-chemists really got a flavour of the way chemists put things together from what Paul was talking about, because it was very elegantly expressed together with the demonstration. Not only put things together, but try to understand the whole of the universe in different ways. And that tour de force, starting and moving through glasses and ending up with a building that Paul has been intimately involved with, I mean, shows both the breadth of silicon chemistry, more importantly, Paul's particular scientific breadth, which I think is actually stunning. There were a couple of things he didn't really mention, as ultrasound. Did a lot of really interesting work using ultrasound to make chemistry work, and that was very well received. And he did mention the biological and medical elements, but you also did work with silicon drugs for quite an amount of time. So didn't have time to talk about the full breadth of what he's done. So massive amount of work there. You will all understand whether you're a chemist or a non-chemist. That and a massive support from all those wonderful students. I was rather late today and had Paul a bit twitchy, I'm afraid. There's very good reasons, I'm afraid to say, but, well, not afraid to say, there's just good reasons. I was thinking as I was running down Exhibition Road, this may sort of repay Paul a little for some nervousness he gave me once. When I've done a couple of his PhD vivas, and one does that as an academic. You examine other people's students for them, and you have to be absolutely scrupulously fair. That, you know, even though I'm a friend of Paul's, that doesn't mean to say that his students get away lightly, and the same applies to me. But there was one young woman that he said. She said that she'd like to appear in national dress for her PhD viva. You remember this one? And I said, oh, that sounds great. And he said, it's a grass skirt. I was waiting for the rest, and he said, just a grass skirt. So we decided that maybe I might not be able to conduct the examination in a proper way, but it had me twitchy for a moment or two. But, so we both moved through Sussex. Paul was a trailblazer then, and I'd just like to recount how we actually met, because we were separated in time by 15 years, although I did DPhil. I also went to Toronto, went back to Sussex. So remarkably similar background. But I got this letter, because we're talking about pre-internet days, really, a letter from somebody explaining that they were a student with Colin Eborn, or I think it was a student at the time, a DPhil student. And Colin had suggested he talk to me because I was at the time doing quite a lot of silicon-29 NMR, one of those sort of techniques, unsung techniques. And Paul was just starting his silanol work, and he thought he'd made trimethylsilanol, which was a really tough one to make. And NMR was one of the characterizing things. And he wrote to me and said, I've got this chemical shift. I think it was about 16.9 ppm, as I recall. Do you think it's trimethylsilanol? And as it happened, I'd been trying not to make trimethylsilanol by an easily hydrolyzable compound, and I'd got this 16.9 shift, which I was 99% sure, so I was able to write back. And then we sort of met and talked, and I came to see him and his family up in Salford at one stage, and so it's a really super pleasure for me to be able to make this. I think one thing Paul didn't really touch on, but is so important to what he does, is I've never met anybody who has got Paul's comprehensive knowledge of the chemical literature, particularly in the silicon. You ask Paul a question and he will tell you that not just the chemistry, but the date and the, you know, who the co-workers were, probably who funded it. He really has that encyclopedic knowledge, which is fantastic. I'm pleased to say it's not just in his head. He has written some of the most influential silicon reviews over the years that there are, some fantastic reviews. I looked up the POS one last night. I think it's now got 650 citations, chemical reviews. Now that's pretty good. 650 people have written papers in which Paul's review has been, and that was with David Cordes, I think.
Yes, David.
Yes.
Who's somewhere. Yes.
Super. Yes, I remember talking when you were writing the reviews. So I was also asked, put some flesh on the sort of person, if you can, for one minute, forgive me, because you know many of you know Paul, but I think it's worth just saying a couple of things about him. So what is it that defines him? Well, he's an overall lovely chap. I mean, you know, no disputing that. He's one of the nicest people one could meet, and at conferences, a pleasure to have a beer or a wine, which you're all saying, well. So he's very outgoing. I mean, one of the things in universities today that characterizes the good professor is a student focus. Paul has got that in spades, both with the undergraduates and the postgraduates. I happen to know various people who've been taught by Paul at both levels, and all have got the most profound admiration for Paul as a student-centered person. Also, he's a public servant. You know, he's done the academic service that a lot of people try and, you know, hide when a committee comes up, but Paul's always been very good at pulling his weight in that, and more than that. He's also, I imagine you're still playing badminton. That was a
Yes.
particular passion, really sporty, you know, you can see he's dying to get out on the badminton court. He's two more things, and then I will stop. Books. He loves second-hand books, particularly chemistry books. I hear sort of some appreciation of that comment. He never goes anywhere without trying to find a second-hand bookshop, you know, some remote town in Poland where we've been, and he's looking for the second-hand bookshop in case they've got a chemistry book. And he's got a wonderful collection, and again, knows that literature very well. But he's not stuck in the book era. That's the interesting thing. Although he collects books, Paul is one of the earliest adopters of IT, but in chemistry that I know. The rest of us were struggling with little PCs, and Paul had this socking great big Apple thing, you know, with three screens.
A long time ago.
Yeah. And he's always adapted and adopted technology, which has made it possible for him to do a lot of the things, visualization of structures, all of that. So he's very much an all-rounder, and very much deserves the huge honour of being a professor at Imperial College, which must be one of the highest academic honours that you can confer on somebody in this wonderful institution. So I'm sure we will all like to express our appreciation